Hi everyone, so it's another data analysis video and I'm continuing with using Python to conduct chi-square tests. So in the previous video I used Python and the scipy stats software library to conduct a chi-square goodness of fit test. So in this video what I'm going to do is build on that a bit and conduct a slightly different test, the chi-squared test of independence. So independence is a key concept in probability where knowing the value of one variable tells you nothing about values of another variable. So the chi-squared test of independence tells you whether two variables are independent of each other. Okay, so with the goodness of fit test, it was kind of analogous to a one sample t-test. We're looking to see if proportions in a sample differed significantly from the population, an underlying population. In this case, we're actually going to look at two categorical variables. So if two variables are significantly associated with each other, we get a significant chi-square result. And in that case, then we would say they're not independent. For example, we may want to assess whether political affiliation varies based on demographic factors such as ethnicity or sex or something like that. And if we get a significant chi-square result, then these variables are significantly associated with each other and are thereby not independent of each other. So in the previous example, in the previous video, I generated some made-up data, and I'll do the same thing again in this video to kind of highlight this. So what I'll do is I'll kind of demonstrate how to manually work this out, calculate the chi-square test of independence, and then we'll use scipy as well. But let's start by generating a little bit of data. So what I'm going to do is I'm going to set a random seed. I'm just going to set that to 10 using numpy np.random.seed. That will allow anyone who wants to kind of duplicate the same results that I get and verify for themselves how this works. I'm going to simulate some demographic voter information to assess independence using chi-squared. So what I will do is create a random sample of data fixed probabilities. So I'm going to create, what I'm going to do is work out, create some data on voter ethnicity, made up data, and then create some data, again made up, on voter party, so their political affiliation, which party they vote for, essentially. And we'll look to see if there's an association between the two. The results will obviously not be real, but it's sort of it'll be useful to illustrate the point of where there's an association between two categories. So what we've got, first of all, in terms of voter ethnicity, I'm kind of creating a categorical variable of different ethnic groups, say in the population, Asian, Black, Mediterranean, other, white, and we're specifying they occur at specific probabilities. So 5% of the population are Asian, 15% are Black, 25% Mediterranean, 5% other, and about 0.5, 50% white. And we're using a sample size of about 1,000. So in this sample of 1,000, we're going to pretend that they were the proportions of different ethnic groups. Similar sort of thing, I'm saving that as an object called voter_ethnic, for voter ethnicity. Similar sort of thing for voter party. We're going to create sample data randomly and specify some fixed probabilities. So I'm going to use the, as I did above here, to create this, generate this made up data, I'm using np.random.choice. Okay, so those are the methods that I'm going to use, np random choice. And I'm going to specify A, which is essentially a list of categories like it was above. This time, in the first sort of object we created, it was a list of categories based on ethnicity. In this case, it's going to be a list of kind of UK political parties, Labour, Liberal, or Conservative, so to speak. And then we'll set probabilities for the counts for each of those three groups. 0.4 for Labour, 0.2 for Liberal, 0.4 for Conservative. Maybe that might actually be pretty close to what it really is in the UK. And then we'll use a similar size as well, size of 1,000, and then What we're gonna do essentially is create a new object called voters, and it's going to be a pandas data frame, and I'm going to pass it a dictionary of key value pairs. The first one is going to be ethnicity, and for that we're going to use the data for that is going to be this list, this voter ethnicity array of counts, proportions, and the second one is party, which was we're going to pass the key as party, and the data is going to be this voter party object we created here. So it's random sample. And then what we're going to do is with this voters data frame object, we're going to create a voters underscore tab, so a cross tabulation of counts of number of individuals falling into each ethnic group based on political party, so to speak. And to do that, I'm going to call this voters object voters.ethnicity, voters.party. Those are the two variables, the names of the two variables. And notice how they've capitalized ethnicity and party, so spot them. So I'm specified margins equals true. So it's going to give us the totals. And I've given, what I'm going to also do is give the names of each of the columns. So voters underscore table dot columns, and I'm passing it a list of what to use. Labour, Liberal, Conservative, and we'll have a row total because we asked for margins to be set to true. And then voters underscore tab dot index. So index would refer to the rows here. So Asian, Black, Mediterranean, or the white, and then we'll have a columns total. Okay, so I'm going to create one other object whilst we're here, but we're going to use this later, and that's something called, I'm calling it observed, and it's going to be, I'm going to use the voter table that we're creating here, and then I'm going to use this .iloc integer location method, and I'm basically asking for rows from 0 to 5 but not including 5, and columns from 0 to 3 but not including 3. So it's basically the same data. It's going to be the same sort of data frame, but I'm only extracting, I'm basically only extracting the political parties and the ethnic groups, and we're missing off the row and column totals. If I run this cell, it's going to create our data, and I'm calling voter tab, so it's going to output this cross tab of the voter information. Let's see what that looks like. So there you go. We get a nice HTML pandas data frame. The political parties are given as columns, the labels for the columns, and we also get the total, which totals along the rows. The row names are different ethnic groups, and we get the column totals as we asked for here. So these are counts, these are number of cases falling into each. So we've got, if we look at political affiliation for, say, people who are Asian, 32% Labour, 32 individuals or participants, observations were Labour, 21 were Liberal, 7 were Conservative, a total of 60 participants. Okay, and we can see here this, you know, if we summed these column totals or either these row totals, we get a total of 1,000, which is correct based on the fact that that's what we asked for as the sample size for in both cases. All right. So for a chi-square test of independence, we use the same formula we use for the goodness of fit test. Okay, the main difference is that we calculate the expected counts in a two-dimensional table instead of a one-dimensional table. So to get the expected count for a cell, we multiply the row total by the column total, and then we divide by the total number of observations, what I often refer to as the grand total. And we can get expected counts for all cells in a table by taking row and column totals, performing an outer product on them, using what's known as the np.outer function, and dividing by the number of observations. Okay, so if I scroll back up, so what I'm saying here is essentially we've got a two-dimensional table. So we've got one categorical variable for representing the columns and one representing the rows. And that differs from when we did our goodness of fit example. We just had two separate columns with a single array in each. Okay, but the calculation is the same as this one here, and it doesn't look great here the way I've typed it, but it's the chi-square, we take observed counts minus expected and square them, sum over all those things, and then we divide by the expected count. And that's how we will calculate our chi-squared value. So let's have a look at this here. So as I said, we're going to calculate expected counts and create a new data frame showing these expected counts. Okay, so I'm going to call this expected, yeah, and we're going to use this np.outer method or function, whatever you prefer to call it, and it's going to be an outer product to work out by. It's going to take the row and column totals essentially to give us the expected counts, and we're going to pass voter tab, which remember was our voter table here, this thing, in as an argument, and we're asking for row totals 0 to 5, and then we're going voter tab dot log column totals 0 to 3. So pretty much similar to what I did above there. Essentially, we are kind of leaving the row total and column totals off. Okay. Right. So. And then we're dividing by the grand total essentially. So what we're doing here is using this function outer, and what it's doing is it's taking the row totals and multiplying by the column totals, yeah, and then divided by the total number of observations, the total number of data points, the grand total. Okay. And then what we'll do is we'll take this expected object and we'll make it into a pandas data frame where the columns are going to be the political party names and the rows are going to be the ethnic groups. If I run this cell, what we get is, if we compare it to the one above, what we're getting now is our expected count. So if you look at those values, they differ and from those essentially. And what this is telling us is, given kind of the size of our sample and our degrees of freedom, essentially, this is what we would expect if this we would expect to see. For Asian people, 25 Liberal, 25 Labour voters, roughly 24 Liberal and 11 Conservative. If these two variables are not associated, they're independent of each other. And we can see that for the others as well there. The values differ from the observed counts. Okay, so to calculate the chi-square statistic, now we've got our observed counts, this table essentially, our expected counts, this table. It's for some reason, I mean, these are nice integers, and these are floating point numbers. I'm not sure what's created them like that, but it doesn't matter too much. It's going to, in terms of us doing mathematical operations on them, it's not going to affect anything. But let's calculate the chi-square test statistic. So I'm going to call it chi_square_stat. And as you've seen previously, we're going to take the observed values, subtract the expected values from them, and then square it. Then we're going to divide by, we then sum this, and we're going to divide by the expected. But as we have this time, we've got a two-dimensional table. We need to run dot sum twice. Okay, so I've got that. So this is an error. It might look a bit weird, but I've got this dot sum. Whereas when we kind of calculated this, let me go back to the example for, where are you? Here we just used dot sum once, but we only had a one-dimensional array. But now things are different, okay, because we've got two variables that we're comparing with each other, that we're looking to see if they are associated. Okay, so I've kind of put a note here on this line that explains what, and we sum twice, what it does is it gives us the column sums the first time, then adds the column sums the second time, so to speak. Let's run that, and what we find we get is a chi-square statistic of 7.17 if if we round that to 2 places, or 7.169 if we did it to 3. Okay, so as I said previously, you know, like so that's our chi-squared test statistic. But we also want to know, is it statistically significant? And in order to answer that question, we need to know what the critical value is, if it's higher than the critical value, and then we can also kind of, given our chi-squared test statistic and our degrees of freedom, we could use the cumulative distribution function to work out what percentage of scores are greater than our statistic. What percentage of scores have a chi-square value greater than ours, and that'll give us our probability essentially. So what I'm going to do here is similar to what I did in the previous video when we did the goodness of fit. I'm going to create an object called crit for critical value. You see it, I'm using the stats.chi-squared.ppf percentage point function method, and I'm passing q the quartile of 0.95 in, and then the degrees of freedom for our data set in this case is 8. So for a 2-dimensional contingency table like this that you're using for chi-square, the degrees of freedom are calculated as the number of rows minus 1 times the number of columns minus 1. So in this case, we've got 5 rows, so 5 minus 1 is 4, and we've got 3 columns, 3 minus 1 is 2. So 2 times 4 is 8. That gives us our degrees of freedom here. Okay, so, or here. So once we've run this, I'm going to print out the critical value and the value that's returned from this particular bit of syntax here, and then I'll do a similar sort of thing underneath where I print the p-value, and we're going to just basically take the complement of our cumulative distribution function. What we're going to do is we're going to take our chi-square statistic 7.17 and use that as our kind of x-axis argument, specify we've got 8 degrees of freedom, and pass it to this cumulative distribution function. If we take 1 minus that, it'll tell us kind of the percentage of scores, the probability of getting that value or higher, that value with chi-squared or higher. Let's run these. What we see is we have a critical value of 15.51 if we round that to 2 decimal places. Okay, so our chi-squared statistic is 7.17, so it's smaller than that critical value. So that tells us it's not going to be statistically significant. And if we look at the p-value, we can see that. So about 0.52, about 52% chance of getting a chi-square statistic this size. Yeah. So what we're seeing here is that there isn't a significant association between between ethnic group and ethnicity and party affiliation. Okay, so what I've just demonstrated there is a manual way to work out the chi-square value, work out the p-value, work out the critical value, in case you might want to know those things. But we can also do the chi-square test of independence using scipy. Okay, and as I showed in the previous example when we did goodness of fit, using scipy, the syntax is much easier. So all that extra code I just did there, we could probably done it much easier by just using the stats.chi-square_contingency and then passed observed in. The only argument we need to pass in is the observed, which is our data frame, our actual this voter tab table, which gives us our observed counts. So we generated our data for ethnicity, we generated our data for party affiliation, and then we created a crosstab to show the counts that fell into each cell. Yeah, and that's the only thing really we need to pass. We need to pass it in when we run this in scipy. So Let me run this. Okay, so what it gives you, interestingly, as output gives you the chi-square test statistic, which matches the one we calculated manually up here. Yeah, 7.17. Gives you the p-value, which matches the one we calculated here manually. Gives you the degrees of freedom, 8 there, and it gives you an array, the kind of expected counts. So you can compare kind of your data frame to the expected counts, and this expected count array will match this one here essentially. Okay, so okay, these results match match the results we obtained in a much more laborious way. Okay, so the only thing you need to be able to do is pass your observed counts, your observed count data into scipy as an argument. Okay, so in summary, what these results I know it's made up data, but what they show is that we've got a non-significant test that indicates that these variables are not associated. So we fail to reject the null hypothesis that they're independent. Okay, so what we're seeing is there is an association between ethnic background of a voter and which party they vote for in this kind of made-up case. That might not be the case in real life, but that's kind of what this data kind of illustrates. So hopefully that's useful. I'm going to stop this video now, and what I'll do is I'll record a third video where I'll do an independence test again on a real data set, but then I will show you what post hoc tests you need to do. So if you get a significant result, kind of how do you interpret where the differences are, or which group is significantly associated with which party, say, or something like that. In this case, it would have been. Okay, I think I've talked long enough on this video. Thanks for listening.